Now, how do we apply this same logic to find the area between curves? Well, I'll start by finding the boundary points of the region, which here are just going to be the intersection points of f of x and g of x. And then I want to think about the rectangles that I'm going to be adding up to produce the full area. In this case, our rectangle has an infinitesimally small width, dx, and it has a height of f of x minus g of x. In this case, the top function, the top curve, minus the bottom curve's height. Now, why is this the case? Well, think about their distances. F of x would run this length, and g of x would run this length. So if I wanted to, I could go ahead and think about this full length, this sub length. If I were to delete this, I would then get the length up top that I wanted, right? So this is f of x, and to delete, we would subtract g of x. This portion would be the f of x minus g of x. Therefore, the area of our shaded region would be the integral from a to b of f of x minus g of x, our height, dx, our base. A common way to think about this problem is just the integral of the top function minus the bottom function. So instead of having to kind of visualize and determine what needs to get subtracted and all that, we just follow the simple top minus bottom rule, and that would give us the area between the curves after we integrate. If we were working in the y dimension, we'd follow a similar procedure, where our rectangle would have some dimensions dy and f of y minus g of y. Note we're taking the full length, the f of y, and subtracting the g of y there. And therefore our area would be the integral from c to d of f of y minus g of y dy. A common way to approach this is we think about this as the right function minus the left function, the right curve minus the left curve.